In other lessons, we introduced three key network elements: the DSL modem, DSLAM, and BRAS. Network elements are devices that make up a digital network. The arrangement and interlinking of various network elements that make up a network is topology. The DSL modem, DSLAM, and BRAS covered the last mile or last several miles of the network, which connects the subscriber's home or office. But there's more in the network that extends beyond the DSLAM and BRAS and towards the worldwide Internet. In order to better understand triple play on DSL, we will take a detailed look at topology of a typical backward-compatible DSL broadband network that connects a DSL customer's home or office through the central office and the communication service provider's network, all the way to the Internet. So why are we interested in a backward-compatible network? DSL network elements have advanced over many generations. However, worldwide, investment has been made in older generations of devices while newer ones evolved. Thus, in current DSL networks, elements with newer technology must remain compatible with older ones. This is backward compatibility. Before we get into the networking details, let us briefly discuss some backward compatibility requirements of DSL network. In earlier implementations of DSL, digital data streams between the DSLAM and the DSL modem were transmitted via asynchronous transmission mode or ATM links. Although DSLAMs and DSL modems have moved away from ATM towards Internet Protocol or IP, many DSLAMs still retain ATM capability for backward compatibility with older local loops and modems. In other lessons, we discussed that the DSLAM terminates multiple local loops connecting various subscribers. The DSLAM aggregates digital data on these multiple local loops and places the data on one or more upstream links. Upstream links are high-capacity links, usually built on gigabit or, in older implementations, asynchronous transmission mode or ATM technologies. Through these links, the DSLAM connects to an element called the Broadband Remote Access Server, or BRAS, that sits at the edge of the communication service provider's network. One key function of the BRAS is to authenticate each subscriber to prevent fraudulent or unauthorized use of DSL services. In the earliest days, the DSLAM used to connect to the BRAS on a single ATM link. Later, it was found that a single ATM link met only the performance needs of Internet access, whereas the video and telephony parts of triple play required more stringent performance that was not met by this single ATM link. Internet access could be best effort, which means that Internet browsing and download related data streams could be slowed down or stopped for short intervals when the DSL network was not performing at its peak, before recovering the streams again. Yet, the subscriber would not mind such short intervals of performance degradation most of the time because as they were browsing or downloading from the internet in bursts, these degradations didn't cause appreciable issues. However, video and telephony over DSL are not forgiving of such performance degradations. So, later generation DSL implementations used separate ATM links for internet access, TV, and telephony data streams between the DSLAM and BRAS. These links were possible due to ATM's switched virtual circuit or SVC architecture. This reduced contention over network resources by multiple services and established priority for video and telephony data streams such that these streams would not slow down or stop when running. Beyond the BRAS and towards the communication service provider's network, the data that the DSLAM aggregated from all subscribers' loops were routed to edge routers over gigabit Ethernet links. In more recent implementations, the BRAS has been merged with another entity called Broadband Network Gateway, or BNG, because the BNG has more functionality over and above BRAS. In our subsequent discussions, we will refer to the BNG rather than BRAS, as BNG is a more contemporary entity. So, to summarize, one of the main backward compatibility requirements for DSL broadband networks is support for both ATM and Ethernet technologies. In the next chapter, we will discuss details of a DSL broadband network designed for triple play. Here is a typical topology of DSL broadband network designed for triple play services, that is, data, video, and telephony. In our example network, the link between DSLAM and DSL modem is asynchronous transmission mode, or ATM, and the uplink between DSLAM and BNG is gigabit Ethernet based. We chose this example since it is a typical scenario in many existing implementations around the world. The DSL local loop between DSLAM and the modem implements ATM as a data link layer protocol over the DSL physical layer. The BNG and the DSL modem use a point-to-point protocol, or PPP, to transmit subscriber traffic. Since the subscriber ultimately connects to the internet, the protocol that the subscriber's data, video, and telephony traffic uses is Internet Protocol, or IP. Thus, the subscriber traffic consists of IP packets. PPP is used to encapsulate these IP packets and tunnel them across the path connecting the DSL modem, DSLAM, and BNG. Note that BNG is typically connected by gigabit Ethernet links, so the PPP frames themselves are encoded into Ethernet frames. The link layer protocol between the DSL modem and DSLAM is Ethernet frames, which carry PPP as their payload, but in this case, the Ethernet frame, that is the PPPoA frame, is encoded within ATM cells. We will cover more on ATM cells shortly. That apart, what we have discussed so far in our example network is a protocol stack. If we map this stack to the OSI 7-layer protocol stack, for the link between DSL modem and DSLAM, DSL is at the physical layer and ATM and Ethernet at the data link layer. For that between the DSLAM and BNG, resilient packet ring or RPR and Ethernet are at the data link layer. Let us take a brief look at DSL, which is at the physical layer between DSL modem and DSLAM. DSL technology can be classified into three groups according to standards laid down by American National Standards Institute or ANSI and European Telecommunications Standards Institute or ETSI. Each group of DSL technology has several variants. Each variant is designed for most optimal performance with a certain loop length, which is the distance of the customer's premises from the central office, maximum data transmission rate, identical or different data transmission rates in upstream and downstream directions, and the type of application, that is, home or business. Symmetric DSL. This kind of DSL allows for the same data transmission rate in both upstream and downstream directions. Some variants in this group are HDSL, SDSL, and SHDSL. Asymmetric DSL. This kind of DSL provides higher downstream data transmission rate than upstream data transmission rate. This design is a common application because many users need higher downstream data transmission rate to allow for faster downloads and page loads in their internet browsers. Following are some variants in this group: ADSL, ADSL2, and ADSL2+. Symmetric and asymmetric DSL. This kind of DSL provides both symmetric and asymmetric data transmissions. Some variants in this group are VDSL and VDSL2. It is common for modern DSL modems to double up as a modem and a router. This device functions as a modem on the WAN side and as a router on the local area network or LAN side. While the WAN side connects the BNG, the LAN side is the subscriber's home or office network, where the subscriber connects their computers and other related devices such as a printer. Such devices in the network are generally called hosts. Let us come back to the protocol stack we described for the WAN. The ATM layer in the stack is a connection-oriented protocol that creates a virtual connection or circuit between two endpoints before data communication commences between the endpoints. ATM utilizes small fixed-size cells into which subscriber data is encoded. These cells are transmitted in virtual circuits or VCs. The VCs are set up between the DSL modem and DSLAM. A virtual circuit is characterized by its virtual path identifier or VPI and virtual channel identifier or VCI pair. Thus, an ATM-based DSL modem has at least one VC specified by a VPI-VCI pair. This is an important parameter from the point of view of configuring the DSL modem, since modern DSL modems that are designed for triple play can support separate VCs for data, video, and telephony. Since separate VCs can be dedicated to data, video, and telephony services, each VC can be configured with the quality of service or QoS contract that is needed for delivery of the concerned service at its optimal quality. Every contract comes mainly in the form of traffic engineering to achieve the desired bitrate demanded by a service. Four basic types of traffic contracts in use are constant bitrate or CBR, variable bitrate or VBR, available bitrate or ABR, and unspecified bitrate or UBR. The protocol stack on the WAN side of the DSL modem establishes an IP network between the DSL modem and the BNG. We can see that it is logical that BNG, being PPP termination for the DSL modem, manages subscriber authentication based on user ID or password credentials which are exchanged via PPP. After BNG performs authentication of subscriber and authorizes for service access, the DSL modem typically receives an IP address on its WAN interface via DHCP. The DSL modem can also receive an IP address by other means, such as from a static pre-configured list. Recall that the modern DSL modem also has a router function that manages the LAN side. For data, that is internet access, the WAN IP address that gets assigned to the DSL modem is typically network address translated to the private IP addresses of hosts on the LAN side according to RFC 1483 routing. The router attached to the DSL modem acts as a default gateway for the LAN, and it allocates private IP addresses to each host connected to the LAN. In our example, the modem and router are integrated as one device. In this arrangement, the modem and router are two electronic modules integrated via an internal bus. Thus, both the modem and router modules are inside the same box. In this case, the NAT between WAN IP address and private LAN IP addresses and RFC 1483 routing are done via the internal bus. As we discussed earlier, the IP packets are encapsulated by PPP. PPP frames are in turn encapsulated by Ethernet frames, and the Ethernet frames are encoded into ATM cells for transmission between DSM modem router and DSLAM. This is designated by point-to-point protocol over Ethernet over ATM or PPPoE/OA. For video service such as TV over Internet Protocol or IPTV, NAT or Network Address Translation is not done in our example. Instead, the WAN IP address is bridged according to RFC 1483 bridging by the router attached DSL modem to a TV host such as set-top box. In this case, the set-top box is assigned the WAN IP address itself. Since the DSL modem router is only acting as a bridging device for the WAN IP, the actual IP path is between the set-top box, DSLAM, and BNG. So IP packets from the set-top box need to be encapsulated by PPP for transmission along this route. But the set-top box is connected to the DSL modem via Ethernet. Therefore, PPP frames must be encoded into Ethernet frames so that the PPP frames can be transmitted between the set-top box and BNG via the bridging DSL modem. As we can see in our example, we have two PVCs set up for two services. One PVC is dedicated to data or internet access, and the other one is dedicated to TV service. Corresponding to the PVC that is meant for data or internet service, the WAN IP is network address translated to the LAN, and the LAN is set up with internet hosts. However, for the other PVC, which is dedicated for video service, the DSL modem acts as a bridging device, and therefore the WAN IP address is not network address translated, but assigned to the set-top box itself. So in our example, we can see that we are maintaining two different PVCs for two different services with separate requirements. One, the data service, the other, video. On the WAN side, the DSL modem is capable of receiving a different WAN IP address per virtual circuit, since each VC sees a separate IP network established via PPPoA. Since each VC is dedicated to a service, every service is accessed on a separate WAN IP network. Because every VC is engineered to provide QoS appropriate for the service it is delivering, the services can be delivered without too much resource contention or quality degradation. The topology of the network between DSLAM and BNG is not DSL based. In our example, it is based on resilient packet ring or RPR. DSLAM extracts the PPPoE frames from ATM cells and transmits them on the RPR. Note that the PPP payload is nothing but the subscriber's traffic. That is, the IP packets originating from the subscriber's LAN via DSL modem router. RPR attempts to take the reliability of connection-oriented digital backbone network communication and combines it with efficiencies of packet-oriented communication. Thus, it is suitable for reliable transmission of Ethernet frames to the BNG. Since RPR is not a DSL standard, we will discuss RPR in another lesson. So, to summarize, we discussed a typical DSL broadband network in which we walked through some key design and topology considerations for delivering triple play services. Fulfillment of triple play with such a network requires allocation and provisioning of network resources, configuration of related parameters, and planning for network capacity and performance.